So in the previous videos we discussed about gravitational field. Now it's time to discuss what is gravitational potential. Let us discuss gravitational potential. First of all, I'll define what is a definition of gravitational potential. I'll tell you what is the definition of gravitational potential. Say if you are given any system of particles, it can be system of discrete particles or it can be system of continuous distribution of particles. It can be system of discrete particles or it can be system of continuous distribution of particles. And we want to find, say, gravitational potential due to this system of particles or single particle or system of continuous distribution of particle. I told you in the last videos that what is system of particles and what is continuous distribution of particles. System of discrete particles means you have bodies like M1, point objects like M1, M2, M3, M4, and system of continuous distribution of masses, mass distributed on a disk, mass distributed on a ring, mass distributed on a sphere, spherical shell. They are continuous distribution of masses. So whatever be the system, it can be system of discrete particles or it can be system of continuous distribution of particles. Whatever be the system, if you want to find, this is your system of particles. It can be system of discrete particles or it can be system of continuous distribution of particles. And we want to find gravitational potential at point P due to this system of particles. See how it is defined, how we define gravitational potential due to a system of particle at point P. The definition goes like: gravitational potential at point P due to system of particles. Gravitational potential at point P due to system of particles is numerically equal to the work done in bringing a test unit mass from infinity to the point P such that the unit mass is never accelerated or it always remains in the state of quasi-static equilibrium. It only remains in the state of quasi-static equilibrium, right? Means if you want to find gravitational potential at point P, then the gravitational potential at point P is equal to work done bringing 1 kg mass from infinity to this point P such that this 1 kg mass is never accelerated. It must always remain in the state of quasi-static equilibrium. Why this condition? Because see, if you accelerate this 1 kg while bringing from infinity to point P, in that case a part of your work done will go into kinetic energy. See, gravitational potential is numerically equal to work done only under this condition. Gravitational potential is a different physical quantity, and work done in another physical quantity. So this equality between these two physical quantities is conditional based on this condition that this unit mass that you are bringing from infinity to point P, it is never accelerated. It is never accelerated. That means when you bring this unit mass 1 kg, this 1 kg is going to experience a force, gravitational force in this direction to this system of particles. This system of particles is going to pull this 1 kg mass in this direction, right? So if you want to keep it in equilibrium, this is your gravitational field G. The force acting on 1 kg mass is called gravitational field. So in order to bring this in quasi-static equilibrium, you must apply the external force such that this F external, such that this plus G is 0, or F external is minus of G. So this work done, which is according to mechanics we know, that is Fext dot dr. So this Fext represented by is minus G. That is equal to work done, and that is gravitational potential. So we call it V. Gravitational potential is denoted by V from infinity to R. Say if I choose a coordinate system, suppose this is at R, right? So work done in bringing the particle of mass 1 kg from infinity to point P such that it always remains in quasi-static equilibrium. So in order to keep it in equilibrium, your external force must be equal to minus of G, minus G dot dr, like this. Get your point? So that's the definition. Gravitational potential is minus G dot dr from reference to point P, and this reference in case of gravitational field is taken to be infinity. Reference means the point where G is 0. The point where G is 0 is taken as reference. So if G has got inverse variation with distance, this reference is going to be infinity, and suppose the position of point P is, that is R from the origin, then this is G dot dr. This is how gravitational potential is found. This is the definition of gravitational potential, right? And G is what? G is gravitational field. If I write its integral form, then G can be written as minus dV by dr here. This is the differential form. This is integral form, relation of V and G in integral form, and this is relation of V and G in differential form. Where this will be useful? This will be useful if I given potential and you want to find field, so you can use this formula. If I given gravitational potential and you want to find field, so you can do it this way, right? And if I given field, you can find potential using this, right? So you can first find field and then potential, or you can find potential and then you can find field from that potential. So this is a relation between gravitational field and gravitational potential. Get your point? This is a relation between gravitational field and gravitational potential. Now I'd like to discuss with you what is the meaning of this quasi-static equilibrium. What is the meaning of this quasi-static equilibrium? What is meant by quasi-static equilibrium? You know what is equilibrium? Equilibrium is a physical state where the net force acting on the body is 0. A body is said to be in equilibrium if net force acting on the body is 0. Then you say it is in equilibrium, mechanical equilibrium. Right? There are many equilibrium like chemical equilibrium, thermodynamic equilibrium, but we are talking about when we say equilibrium over here, we mean to say mechanical equilibrium. So a body is said to be in mechanical equilibrium if net force acting on that body is 0. Then what is quasi-static equilibrium? Quasi means what? Quasi means something like false. Quasi means false. Quasi-static equilibrium. So what is quasi-static equilibrium? See, this word of quasi-static has come from thermodynamics. The word quasi-static has come from thermodynamics, right? So the good example to understand this quasi-static equilibrium will come from thermodynamics itself. So I'll take an example of thermodynamics and tell you what is quasi-static equilibrium. Suppose we have a say container like this, a vessel. This is the vessel, and this has got a say piston. You have a piston over here. Okay, suppose this piston is light. Light means the mass is negligibly small. So at equilibrium, P in, suppose this contains an ideal gas. So at equilibrium, the force acting on the piston from downward side is P into area of the piston. This is P in, and from upward direction the force acting is P ATM into area, right? So at equilibrium, this P in into area will be equal to P ATM into area. That is, P in is equal to P ATM. Now suppose we have a heap of sand particle. There is a heap of sand particles over here. You know what is sand particles? You have a heap of sand particles over here. Alright, so there is a heap of sand particle, and I give you a task. The task is to pick one sand particle and put it over here. Just pick one sand particle and put it on the piston. What will happen? You just pick one sand particle and put it on the piston. So what will happen now? See, what is the mass of the sand particle? It's very small. It can be say 1 milligram. Mass of this piston, mass of the sand particle would be say 1 milligram, right? So the mass of the sand particle is very small. But howsoever small it is, you have a force. It will exert a force on this piston, and that is equal to mg. Though m is very small, but it is going to exert a force on the piston, that is mg. Alright, get your point? And this force will bring a case of disequilibrium in the piston. Now instead of this we have mg also. So the right hand side increases. So as a result of which, what will happen? The piston will come down slightly. Why slightly? Because the moment piston comes down, the volume decreases, and I assume that temperature is constant throughout. So the moment piston comes down, the volume decreases, your P in increases, and P in does not have to increase much, because the moment P in increases, this again becomes equality. Since this mg is very small, m is mass of sand particle, it creates a case of disequilibrium. It exerts a force in downward direction. So piston will come down slightly in downward direction, and it has to come slightly only because the moment piston comes down, the volume decreases, and the volume decreases is pressure inside increase. Pressure inside increase, right? And the pressure doesn't have to increase by a very high value, because the moment pressure increase, this become equality. Piston will come down by slight value, right? Now don't stop over here. You just put one more sand particle. Again the piston will come down slightly. Again the piston will come down slightly. It will come down by so small value that you won't be able to observe it. This is milligrams, right? So it will come down slightly, but it will be very hard for you to observe piston coming down slightly. And now you keep on doing this, and you put one by one all the sand particles over here. It will take many hours, even a day also, and you will find that piston is not moving. Piston is moving down slightly, but you won't be able to observe it. It is so small. But by the time you put all the sand particle over here, you'll find that your piston has come down by a considerable value. Five centimeter. Just again typically.
By the time you put all the sand particle in the piston would have moved by say 5 centimeter. But this journey of 5 centimeter is not immediate. If suppose we have here 10 raised to the power 6 sand particles, then journey of 5 centimeter is carried into 10 raised to the power 6 sub processes. This process of journey of 5 centimeter is carried out through 10 raised to the power 6 sub processes, and in the beginning and in the end of each sub process the piston is in equilibrium. The piston is not equilibrium in continuity. It is broken into, the journey of 5 centimeter is broken into, if you have 10 raised to the power 6 sand particle, it is broken into 10 raised to the power 6 sub processes, such that at the beginning and at the end of each sub process piston comes in equilibrium. So this journey of 5 centimeter is dotted by 10 raised to the power 6 sub 10 raised to the power 6 equilibrium position. The journey of 5 centimeter is dotted by 10 raised to the power 6 equilibrium positions. So you have equilibrium not in continuity, but it's equilibrium in discontinuity, but there are lots of equilibrium position in this journey of 5 centimeter. And through in each sub process the piston travels a distance of this. Since 5 centimeter is broken and divided into these number of sub motions, so each motion takes place by this 5 into 10 to the power minus 6 centimeter, and this distance is not observable. This is very small, and this process is quasi-static equilibrium. This is called quasi-static process. This is called quasi-static process. So the journey of this 1 kg from infinity to point P is this kind of process. It is this kind of process that takes place. Alright. So that is meant by what is quasi-static equilibrium. It's not equilibrium in continuity, it's equilibrium in discontinuity. Alright.